Hey everyone, I'm Eli, and today I'm going to walk you through my latest project, which was building a variational quantum eigensolver. So, a variational quantum eigensolver is a hybrid quantum classical algorithm, which means part of it runs on a quantum computer and part of it runs on a classical computer. Specifically, for variational quantum eigensolvers, we're trying to optimize for the lowest ground energy of a molecule. So to do that, we model the molecule on the quantum part and then do the optimization on the classical part. So the optimization part is very much like machine learning, which if you've watched some of my previous videos, you'll know a little about. To build my VQE, I used a library called Pennylane, which is designed to make doing quantum stuff, both on simulators and on real quantum hardware, really easy in Python. I imported NumPy from Pennylane because it's a slightly different version than standard NumPy. And I also imported QChem, which is the quantum chemistry library of Pennylane. So the first thing I did was have my symbols. So I modeled an H2 or a hydrogen molecule. So I had my symbols be H and H for hydrogen. I then set the coordinates to be basically the distance that the two atoms are apart from each other. I just used an online database for this. I then used QChem molecular Hamiltonian on the symbols and coordinates to find both the Hamiltonian for this molecule using the Hartree-Fock approximation and the qubits I will need to model this molecule. So I printed it out, and as you can see, we'll need 4 qubits. I then found the Hartree-Fock state, which we will use as our initial state, which we will then hopefully optimize on to find an even lower energy ground state. So here our Hartree-Fock state is 1100, and as we'll see, we can have a lower energy than that. I then wrote 3 functions that will help me run my VQE. The first is my circuit function, which builds my quantum circuit. The first thing I do is set my basis state, so basically this takes my Hartree-Fock state and puts it onto my qubits. I then use a double excitation gate, which you'll notice is parameterized, and that is what we will be optimizing on, that parameter. So the way it works is it takes 2 qubits and superpositions them, a superposition of 4 qubits. So this is where we're getting our superposition from. That's also what we'll be optimizing on to find the best superposition. The next function I needed was my cost function, which again, taking a parameter that will later be called theta, calculates the circuit for that theta, and then returns the expectation value for that state. The expectation value is basically what energy we expect to get from that state. Since it's quantum, it will be probabilistic, which is why we have to take the expected value as opposed to just measuring it once. The third function is the ground state function, which we will use only at the very end, and it will tell us, based on our optimized parameter theta, what the actual ground state is, as opposed to just what the energy in that state is. I then used a loop to run it. So I used gradient descent on my classical side, and then the classical side parameterized theta, which is what we're adjusting our double excitation gate based off of, and fed the new value of theta into the quantum, which then fed the results back into classical, and so on. We eventually converged to an energy of negative 1.137 Hartree. We can then take a look and see what our final theta was to get this low energy, and our final theta was 0.225 radians approximately. Finally, we can then run our ground state function to see what the actual ground state is, not just the energy in that state. So we get this matrix that looks like a lot, and it was pretty overwhelming to me. The key here is that Pennylane expresses the states in matrices that are organized basically alphabetically. So 0000 comes before 0001. And from there you can construct the whole matrix. And using that, I found that our ground state was 0.9941100 minus 0.1120011. So that's how I built a variational quantum eigensolver and calculated the ground energy and ground state for a hydrogen molecule. I hope you enjoyed this video, and if you did, please like and subscribe. If you're interested in more in-depth musings on quantum computing and AI, check out my Medium account where I have articles that are more in-depth than my videos. And if you're interested in following my progress in quantum computing and general problem solving, subscribe to my newsletter for monthly updates. Thanks.